the development of formal logic. Once thinking had come to be regarded as a form of computation, its formalization and eventual mechanization were obvious next steps. As noted earlier, Gottfried Wilhelm von Leibniz, with his Calculus Philosophicus, introduced the first system of formal logic, as well as proposed a machine for automating its tasks. Furthermore, the steps and stages of this mechanical solution can be represented as movement through the states of a tree or graph. Leonhard Euler, in the 18th century, with his analysis of the connectedness of the bridges joining the riverbanks and islands of the city of Königsberg, introduced the study of representations that can abstractly capture the structure of relationships in the world, as well as the discrete steps within a computation about these relationships. Euler, 1735. The formalization of graph theory also afforded a possibility of state-space search, a major conceptual tool of artificial intelligence. We can use graphs to model the deeper structure of a problem. The nodes of a state-space graph represent possible stages of a problem solution. The arcs of the graph represent inferences, moves in a game, or other steps in a problem solution. Solving the problem is a process of searching the state-space graph for a path to a solution. By describing the entire space of problem solutions, state-space graphs provide a powerful tool for measuring the structure and complexity of problems and analyzing the efficiency, correctness, and generality of solution strategies. As one of the originators of the science of operations research, as well as the designer of the first programmable mechanical computing machine, Charles Babbage, a 19th century mathematician, may also be considered an early practitioner of artificial intelligence. Babbage's difference engine was a special-purpose machine for computing the values of certain polynomial functions and was the forerunner of his analytical engine. The analytical engine, designed but not successfully constructed during his lifetime, was a general-purpose programmable computing machine that presaged many of the architectural assumptions underlying the modern computer. In describing the analytical engine, Ada Lovelace, 1961, Babbage's friend, supporter and collaborator, said, "We may say most aptly that the analytical engine weaves algebraical patterns just as the jacquard loom weaves flowers and leaves. Here, it seems to us, resides much more of originality than the difference engine can be fairly entitled to claim." Babbage's inspiration was his desire to apply the technology of his day to liberate humans from the drudgery of making arithmetic calculations. In this sentiment, as well as with his conception of computers as mechanical devices, Babbage was thinking in purely 19th century terms. His analytical engine, however, also included many modern notions, such as the separation of memory and processor, the store and the mill in Babbage's terms, the concept of a digital rather than analog machine, and programmability based on the execution of a series of operations encoded on punched pasteboard cards. The most striking feature of Ada Lovelace's description, and of Babbage's work in general, is its treatment of the patterns of algebraic relationships as entities that may be studied, characterized, and finally implemented and manipulated mechanically, without concern for the particular values that are finally passed through the mill of the calculating machine. This is an example implementation of the abstraction and manipulation of form, first described by Aristotle and Leibniz. The goal of creating a formal language for thought also appears in the work of George Boole, another 19th century mathematician, whose work must be included in any discussion of the roots of artificial intelligence. Although he made contributions to a number of areas of mathematics, his best-known work was in the mathematical formalization of the laws of logic, an accomplishment that forms the very heart of modern computer science. Though the role of Boolean algebra in the design of logic circuitry is well known, Boole's own goals in developing his system seem closer to those of contemporary AI researchers. In the first chapter of An Investigation of the Laws of Thought, on which are founded the mathematical theories of logic and probabilities, Boole, 1854, described his goal as to investigate the fundamental laws of those operations of the mind by which reasoning is performed, to give expression to them in the symbolical language of calculus, and upon this foundation to establish the science of logic and instruct its method, and finally to collect from the various elements of truth brought to view in the court of these inquiries some probable intimations concerning the nature and constitution of the human mind. The importance of Boole's accomplishment is in the extraordinary power and simplicity of the system he devised. 3 operations, and, or, and not, formed the heart of his logical calculus. These operations have remained the basis for all subsequent developments in formal logic, including the design of modern computers. While keeping the meaning of these symbols nearly identical to the corresponding algebraic operations, Boole noted that the symbols of logic are further subject to a special law to which the symbols of quantity, as such, are not subject. This law states that for any x, an element in the algebra x times x equals x, or that once something is true, repetition cannot augment that knowledge. This led to the characteristic restriction of Boolean values to the only 2 numbers that may satisfy this equation, 1 and 0. The standard definitions of Boolean multiplication and addition all follow from this insight. Boole's system not only provided the basis of binary arithmetic, but also demonstrated that an extremely simple formal system was adequate to capture the full power of logic. This assumption and the system Boole developed to demonstrate it form the basis of all modern efforts to formalize logic. From Russell and Whitehead's Principia Mathematica, through the work of Turing and Gödel, up to modern automated reasoning systems. Gottlob Frege, in his Foundation of Arithmetic, created a mathematical specification language for describing the basis of arithmetic in a clear and precise fashion. With this language, Frege formalized many of the issues first addressed by Aristotle's logic. Frege's language, now called the first-order predicate calculus, offers a tool for describing the propositions and truth value assignments that make up the elements of mathematical reasoning and describes the axiomatic basis of meaning for these expressions.